Okay, this video is going to be all about static equilibrium, okay? Or, yeah, static equilibrium. I'm going to talk about dynamic equilibrium at the end of this. I'm actually going to write myself a note before I forget. Dynamic equal, there, at the end. So the best way to kind of teach you guys about static equilibrium is to kind of go through some practice problems. So the definition of static equilibrium means that first, the system is at rest. Okay? So our translational velocity is 0 and our rotational velocity is 0. Okay? So in order for that to be true, we have two things that need to be true. The net force acting on the system has to be 0, and the net torque acting on the system has to be 0. Okay? So those are the kind of equations we're going to focus in on now, net torque and net force equations. So in this first example, we kind of have a straightforward seesaw problem. So the first thing I'm going to do is I'm going to draw the forces acting on the board. Just the forces acting on the board. So acting on the board, I have an upward force from this fulcrum, which I'm going to call Fs for F support. And then at about that location, the center, I have a force of gravity of the board. Okay? Then the additional forces that I have are the force of gravity acting on this 2 kilogram mass. So the force of gravity pulls the 2 kilogram mass onto the board, and that causes a downward force on the board, which happens to be equal to the force of gravity acting on the 2 kilogram mass. It's essentially the downward normal force from the 2 kilogram mass. And then there's also a downward force of gravity from that 5 kilogram mass. Okay. So again, we know that in order for this system to be at rest, my net forces need to be 0 and my net torques need to be 0. Now looking at this problem, it looks like I need to figure out how far the 5 kilogram mass is from the fulcrum. Now the reason why I have it labeled from the fulcrum is because that fulcrum is my axis of rotation. Since I'm looking for that distance, that gives me a pretty good hint that I'm going to need to focus in on torque first, since torque is the only thing that deals with forces at a distance. Okay, so this FG2 is going to create a negative torque, and FG5 is going to create a positive torque. FG2 is clockwise, FG5 is counterclockwise. Remember, you can take the force and rotate towards equilibrium, and that gives you your direction of rotation. Okay, so I'm going to have the torque from the 5 kilogram mass minus the torque from the 2 kilogram mass equals 0. Okay, so I'm going to go ahead and rearrange this now, so I end up with torque from 5 kilogram is equal to torque from 2 kilogram. Now remember, torques are forces, Fg5, times distances. Again, a lot of students forget that distance part, so don't be a lot of students. Be extraordinary. Okay, so Fg2 times 3 meters. Okay, remember, the force of gravity acting on an object is just its mass times the acceleration due to gravity, which I'm going to abbreviate as 10 to make the math easier. Okay, and Fg2 would be 2 kilograms times 10 meters a second times 3 meters. Okay. So this gives me 50x on this side, and then 20 times 10, that gives me 60. Okay, so I'm going to divide both sides by 50, and I get x is 6/5, which I'm pretty sure is 1.2, but I'm going to get my calculator out right now. Yep, it is 1.2 meters. So in order for this teeter-totter to be balanced, the 5 kilogram mass needs to be placed at a distance of 1.2 meters from the fulcrum. Anything other than that, and this system is no longer going to be at rest, it will start to rotate. Okay, so I actually didn't need to look at any net force equations here, which is nice. Okay, so this is the simplest equilibrium problem we might come across. Okay. The next hardest problem might be our standard window washer problem. So in this problem, we are usually looking for the tension in the two support cables. Okay. So again, we're going to start with a free body diagram. So I'm going to label this as T1, and I'm going to label this as T2. Okay. Then it looks like the board that the person is standing on has mass. So I'm going to label that as FG and B. And I'm going to remind myself that that's at a distance of L over 2. Okay. And then the person, remember, creates a downward force equal to their weight. And it looks like that is at a distance of 4/5 L. Okay. So I'm looking for the tensions. Now, it's not immediately obvious whether I need to use forces or torques, so that probably means I need to use both. Okay, so let's start with torque. Okay, in order for me to be able to apply a net torque equation to this type of problem, I need to pick an axis of rotation. Since the distance of the person is based off of this left-hand string, that's what I'm going to make my axis of rotation. Okay. What that also does is it makes it so that T2 does not produce a torque. So in my equation for torque, I won't have to take into account T2. Okay. Next thing I want to do is figure out direction. So T1 is going to be positive, FGP and FGB are going to be negative. Okay. Again, I'm looking at torques first. Okay. So I'm going to have a torque from T1 minus a torque from the board minus a torque from the person. And that's all going to equal 0 because this whole system is at rest. And I'm going to continue this down here where I have a little bit more room. Okay. So I'm looking for T1. So I'm going to go ahead and rearrange now while my algebra is a little bit simpler for the torque from T1. So FGB plus torque from the person. Okay. Now remember, torques are forces times distances. So the torque from T1 is T1 times the distance from the axis of rotation, which is the whole length of the board. Okay. Torque from the board would be FG of the board times L over 2. Okay. And then for the person, this is FG of the person times 4/5 L. Okay. Awesome. Now, if I look right now, there is an L in every single term. I have one here, and one here. And if there's an L in every single term, obviously, like you could circle it, then that means it can go ahead and cancel. The fractions still stay, but the actual variable L can cancel, which is great because I don't know what L is. So this becomes T1, okay, 1/2. I'm just going to pull out that 1/2 out front to make my life easier, plus 4/5 FGP. Okay, so T1 is 1/2. The mass of the board was 100 kilograms. I have it written right here. Okay. So 100 kilograms times G, which is 10. And then plus 4/5. The mass of the person was 75 kilograms. Okay, so 75 kilograms times 10 meters a second squared. So this is 500. I don't know what 4/5 times 75 times 10 is quite yet. So 4/5 times 75, times 10 is 600. All right, so that gives me T1 is 1100 newtons. Okay. So now that I have T1, I need to figure out what T2 is. Okay? And there's actually two ways for us to find T2. We could redo this torque problem, but just shift our axis of rotation to the right-hand side, because that would get rid of T1 in our equation, which is more than correct. Or we could use a net force equation, because we know that all of the upward forces, T1 and T2, have to balance with all of the downward forces. And again, I'm talking forces, not torques. Okay, so this keeps the object from moving linearly, essentially falling up or down. Okay, so T1 was 1100 newtons. I'm looking for, actually, you know what, before I plug in, let me rearrange for T2 to make my life easier. So T2 is going to be force of gravity of the person plus the force of gravity of the board minus T1. There we go. So T2, person was 75 kilograms times 10 meters a second squared gives me that FG. The board is 100 kilograms times 10 meters a second squared gives me that. And T1 was 1100, which we found out. So this is 750 plus 1000 minus 1100. T2 is 650 newtons. Okay, and that makes sense. T2 should be less than T1. The person is closer to T1, so T1 has to work a lot harder than T1 to keep the whole system balanced. Okay. All right, so that's a little bit more complex problem. The next type of problem we might see is a problem like this, where we have a sine problem with some sort of cable at an angle. And I didn't label it, but let's say that this cable is attached at, I don't know, let's come up with a fun fraction. 4/7 L. Why not? Okay. So with these sine problems, we're often looking for the forces from the hinge or the tension in the cable, or a little bit of both. Okay, so let's draw a free body diagram. Okay, so we have a downward force from the sine. Okay, we have an angled force of tension. We have a force of gravity from the rod, okay, which I've labeled as R, rod. Okay, we have a horizontal force from the hinge, and we have a vertical force from the wall, okay, or from the hinge as well. Okay, so we have a horizontal force from the hinge and a vertical force from the hinge. Now, I don't know if the vertical force from the hinge is going to be up or down, so I'm just going to take a guess. I'm going to say that this is down. Okay. So again, let's say that we're asked to find tension and these two forces. Okay. So again, we're going to need to look at net torques and net forces. Okay. So I'm going to start with torques. And the reason why I'm going to start with torques is because when I use that torque equation, I can usually get rid of some forces. Because I'm going to say my axis of rotation is right here, which means that FH and FV do not produce torques because they are at a distance from the axis of rotation. Okay. It also means that the tension force produces a positive torque, and the two downward forces produces negative torques. Okay. So I'm going to have the torque from the tension minus the torque from the rod, the weight of the rod, minus the torque from the sine, or the weight of the sine. So my tension torque is going to equal torque from R minus plus the torque from the sine. Okay. Now, that tension torque, the tension's at an angle. So really, it's only the perpendicular component that's producing a torque. So that means I need to include that sine in my equation. Okay, meaning the sine of 30. So this would be T. It's occurring at 4/7 L, okay, times the sine of 30 degrees. Again, that sine of 30 takes into account the perpendicular component. Okay? The rod is FG of the rod, L over 2, because it occurs at the center, plus the force of gravity from the sine, and that occurs at L. Okay? Again, we see the letter L in every single term, which means it can go away, which makes our life easier. Okay, so I'm going to rewrite these. Okay, so this is 4/7 t sine 30. 1/2 force of gravity from the rod plus force of gravity from the sine. Okay. Other thing to remember is that the sine of 30 is 1/2. So I can actually combine the 1/2 and the 4/7. When I'm multiplying fractions, I multiply the top and then I multiply the bottom. So this is 4/14 t is 1/2. The mass of the rod is 10 kilograms times 10 meters a second squared. Sine is 5 kilograms times 10 meters a second squared. Okay, so this is 4/14. 1/2 times 10 times 10 is 50. This is a t, I forgot that. Plus 50. So 4/14 t is 100. I'm going to multiply by 14/4. That's a fun fraction. Okay, so the tension is 1400 over 4, which hopefully that's not divisible by 4, but it's okay. By 4. Oh, it is divisible by 4. How exciting. It's 350 newtons. That's big tension, but that's okay. Okay. All right. So then we have to figure out the horizontal and vertical forces from the hinge, and that's when we use net force equations. Okay, but I'm not just going to use one net force equation. I need one in the x direction and one in the y direction. So my x direction forces, I have the parallel component of the tension and the horizontal force from the hinge. Okay, so I have FH minus tension parallel. Okay, vertically, I have the tension, the perpendicular tension upwards, FG, FG, and FV downwards. So this is FT perpendicular minus the vertical force from the hinge minus FG of the rod minus FG of the sine. Okay. All right, let's do the x direction first since there's less there. Okay, so this says that the horizontal force from the hinge equals the parallel or x component of the tension, okay, which is going to be the tension times the cosine of theta. So that's going to be the 350 newtons times the cosine of 30 degrees, which is going to be a number that's going to be ugly because the cosine of 30 is not as nice as the sine. Where's my calculator? All right, so we got 350 times the cosine of 30, making sure I'm in degrees, and I am. So horizontal force is 303.1 newtons. Okay, so the wall is pushing out with 303.1 newtons. Now let's go ahead and figure out the vertical force, FV. So I'm going to go ahead and rearrange for that first by adding it to both sides. So the perpendicular component of the tension minus FGR minus FGS is the vertical force from the hinge. Okay, so this is that tension force times the sine of theta minus FGR minus FGS is FV. So 350 times the sine of 30 minus the rod was 10 kilograms. Kilograms times 10 meters a second squared, mg. 5 kilograms times 10 meters a second squared, that's another mg, is FV. Okay, so 350 times the sine of 30 is 175 minus 100 minus 50 is FV. Okay, so 175 minus 100 minus 50. The vertical force from the hinge is 25 newtons, and the fact that I got it positive means that my initial direction of downward that I chose is correct. If I had gotten a negative number here, it just means that the direction that I had chosen was incorrect and it would have actually been up. Okay? So that's another way to practice these. Okay? The last type of problem we might see is a ladder problem. And I'm not going to go through and actually solve. I'm just going to set up equations for this one. Okay. So for a ladder problem like this, okay, we have a downward force of gravity from the person. We have at the center downward force of gravity from the ladder, not letter. We have a normal force from the wall. That's a W. Okay, we have, let's say, an upward friction force from the wall, and it's static friction because we're at rest. Okay, and I say it's upward because if this is going to slide, the ladder will likely slide downwards. Same thing here. If this is going to slide, the ladder will likely slide to the left. So I'm going to say that friction points, I'm going to call this FFSG, meaning ground, and this is the wall. Okay. And then we have a normal force from the ground. Okay? Lots of gross forces. Okay. So, net torque, net force. Super fun. Let's start with net torque. Okay? I'm going to say that my axis of rotation is this bottom point here, which means the normal force and the force of friction from the ground do not produce torques. Okay? FGL and FGP produce negative torques. Force from the wall and the force friction from the wall produce positive torques. Okay. So, we have the torque from the force of friction from the wall plus the torque from the force on the wall. Okay. Minus the torque from the force of gravity on the person minus the torque from the force of gravity on the ladder. Okay. Now in this, we don't really know what we would be looking for. I'm just showing you equations set up. Okay. So force of friction on the wall, it would be FFSW times L. It's at that total distance L. But here's the thing. It is not perpendicular to our axis of rotation. Sorry, my cats just ran out the room. Okay. So let's say this angle down here is theta, which makes that this angle is also theta, and this angle here would be 90 minus theta. Okay. So I would actually need to use, in my equation, since my angle with the lever arm is 90 minus theta, that's when I would use cosine theta. The force from the wall, okay, is an angle of theta from the ladder, so I can use sine there. Okay. Now, the forces of gravity are, so this is from the person, so that's 5/6 L, and this would be another instance, okay, where this angle in here, same here, would be 90 minus theta. Okay, and I can get that because if I drop down these, it becomes one big right triangle. And if these angles are 90 and this bottom base angle here is theta, then these have to be 90 minus theta. Okay, so both FGs also need to use cosine of theta, since the sine of 90 minus theta is the same thing as the cosine of theta. So minus force of gravity of the ladder, L over 2 cosine theta is 0. Okay. This friction force would really be static coefficient of friction times the force on the wall, okay, because that's the Fn at that location. L cosine theta plus FWL sine theta minus pulling the coefficients out front, FGPL cosine theta minus 1/2 FG ladder L cosine theta. So that's the net torque equation. That makes my head hurt. But it looks like in order to solve this for anything, I would need to know Fw. So I'm going to find Fw by looking at a net force equation in the x direction. So in the x direction, again, I'm just thinking like left-right. I have the force of friction from the ground and the force from the wall. Okay, so the force of friction from the ground is equal to the normal force from the wall. So this is mu s Fn is Fw, but here's the thing, I need Fn. Okay, so I need to look at a net force equation in the y direction. Y direction, my upward forces, I have a normal force, I have a force of friction from the wall, okay? And then my downward forces, I have a force of gravity from the ladder, force of gravity from the person. Okay, so I have Fn plus mu s Fw FGL FGP. Okay, so it looks like I have basically two unknowns in all of my equations, or in this equation, I have Fn and Fw that are unknown. So what we could do is we could take this equation for Fw and substitute it in. Okay, so we could say that this is Fn plus mu s Fn, and so on. Same thing up here for Fw. And that would allow us to figure out what this normal force is. Once we know that normal force, we know Fw, and we can substitute it in up here to solve for whatever we need to solve for. Okay. Again, I'm not going to go through and do that because that's probably more complex than the AP exam will get into, but I wanted to make sure we went over it. Okay. The last thing I wanted to talk about is dynamic equilibrium. So dynamic equilibrium, we still have a net force equal to 0 and a net torque equal to 0. But in either of these situations, we're either moving at a constant linear velocity and at rest rotationally, or we're at rest linearly and omega is constant. Okay, or we could have both. V is constant and omega is constant. So that would mean the net torque and the net force are 0. So if you see any of these situations, it means this. Okay? So essentially when you are not accelerating. So let's say we had, I don't know, this weird like pinwheel thing. And it's on a stand and it is rotating at some constant angular velocity. Okay, so no linear motion, just rotational motion. Okay, but this is constant. Okay, so if it's constant, that means my net torque is 0. So let's say I have a force being applied to this outer edge here, a force F. Okay, and I want to know if I am applying another force at a distance of 1/3 L. So let's say each of these has a length of L. What should the value of this force be so that that constant angular velocity is still holding true? Okay. Now, actually, this situation we can solve in the same way that we solved for that first seesaw problem where the whole thing was at rest. Okay. The only difference is that we have this constant angular velocity, but it doesn't change our equation. Okay. Our axis of rotation is this center point here, and we have two lever arms, which is totally fine. Doesn't change anything about our problem. Okay, both forces are going to be perpendicular to the lever arm. Awesome. This force creates a negative or clockwise torque. This one creates a positive or counterclockwise torque. Okay, so my torque from my unknown force minus my torque from my force F has to equal 0 because I'm rotating at a constant velocity. Okay. So I'm going to call this unknown force X to make my life easier. Okay. And so this is my torque from X has to equal my torque from my force F. So the force X at 1/3 L has to equal my force F at L. Okay. There's an L in both terms, so I'm going to get rid of it. And I'm going to pull this coefficient out front. Okay. So it looks like X, I multiply both sides by 3, has to be equal to 3F. Okay. So really, this problem is not any different than the ones we did before. The only difference is that we are moving at a constant angular velocity. So when you see that word constant angular velocity or even constant linear velocity, I would write out net torque is 0 or net force is 0, just to remind yourself that that is an option. And that is it for this equilibrium video. Have a good day.